You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Patrick Lukavka. Patrick Lukavka is a Brazilian-Italian planetary scientist and dynamicist at the Kindai University in Japan. He has contributed to various topics in planetary science, and his areas of research include the origin and evolution of the solar system, physics and dynamics of solar system bodies, terrestrial planet formation, and planetary migration.
Patrick Lukavka, welcome to the program.
Thank you for inviting me.
Now, Doctor, there's been some talk over the last 3 or 4 years, actually, of strange patterns of movement objects in what seemed to be perturbed orbit in the Oort cloud, which led to a hypothesis about Planet 9. But in this case, we're talking about something a little bit different. What differentiates this from the Planet 9 story?
Okay, the first difference is that we are not considering orbital alignments of distant trans-Neptunian objects or Kuiper objects, in particular beyond 150 or around 250 astronomical units, which was the main motive for the Planet 9 hypothesis. So that's the first difference. Our observational constraint is that we started with is different. We don't consider this, let's say, strange orbital alignments. And as we discussed in the paper, we mentioned some previous studies that they question the validity of these alignments. So in that sense, in my opinion, this is still a matter of debate. Maybe they are real, maybe they are not. They are just observational biases. So in our study, we consider a different observational constraint which are not in dispute, which are essentially some groups of Kuiper belt objects located beyond 50 astronomical units, which I called the distant Kuiper belt. So what we did initially, we identified actually some populations at these distances. For example, this was not the first time we identified such population, but this time we did in a more rigorous way. So we identified, for example, a prominent population of TNOs, trans-Neptunian objects or Kuiper belt objects. I'm going to use TNOs as for abbreviation of Kuiper belt objects. So a prominent population of TNOs with orbits beyond Neptune's gravitational influence. So in particular, those that have perihelion distance, which are the closest approach of the orbit to the Sun, beyond about 40 astronomical units. So this was the first population we identified more rigorously. And the second population was a statistically significant population of TNOs with orbital inclinations higher than 45 degrees. And this is because in the current solar system, it's difficult to explain TNOs in the distant Kuiper belt with such high inclinations. So at this time, we argue that there is a statistically significant population with such high inclinations, which we call also high I, or high inclination TNOs. And the third population, which is actually a subpopulation of those two populations I just mentioned, are TNOs with extremely peculiar orbits. Such, for example, they appear to be some of them appear to be so distant that they seem to be detached from the solar system. And I think the most famous member of this subpopulation is Sedna, object Sedna, which has a perihelion distance of about 76 AU. It's very distant from Neptune. And the single discovery of these objects already called for revision of our understanding of the outer solar system, because the current solar system, the perturbation of the giant planet Sun on, they cannot explain such a peculiar orbit. But in this paper, we also identified other TNOs with very peculiar orbits in addition to Sedna. We list actually 10 objects, and some of them, they have actually very high orbital inclinations, higher than, for example, 60 degrees. So it's even more difficult to explain such high inclinations in the distant Kuiper belt. And finally, we also identified a fourth population, in the distant Kuiper belt, they represent an important group of primordial stable resonant TNOs. So what I mean by that, resonant TNOs are objects that display mean motion resonance dynamics with Neptune. So, for example, maybe the most famous member is Pluto. Pluto is currently in the what we call the 3-to-2 mean motion resonance with Neptune. So, in simple terms, when Neptune completes 3 orbits, Pluto completes 2. So, in the distant Kuiper belt, we identified several stable such resonant TNOs, but they are locked in other resonances, not 3-to-2, other more distant resonances. And it turns out that this population is very important because they are stable. And by stable, I mean they have been under resonant motion for billions of years. So that means that if there is any hypothetical planet located beyond 50U or 100U, whatever the distance, the perturbations of this planet could destroy the stability of these primordial resonant TNOs. So we identified and published in the paper several of these objects, and they are important because they can constrain the maximum approach of any hypothetical planet. Otherwise, these stable populations they could be destroyed. So they are very important. So in this paper, the identification of these stable resonant TNOs allowed us to place a minimum distance that the hypothetical planet should have, or in other words, the minimum perihelion, the minimum closest approach. It turned out to be for an Earth-like planet, which I mean a planet with mass or size similar to Earth. It turned out to be about 200 AU. So that means the planet has to be perihelion larger than 200 AU. Otherwise, these stable resonant populations they can be destroyed, and so which will be, of course, in conflict with observations. So that's, in summary, that's our observational constraints. Our goal was to try to explain how these 4 groups of TNOs they came about, because the current solar system cannot explain them. They are very peculiar, very strange in that sense. And by the way, if I can continue, we actually look at the literature for especially representative models of solar system or outer solar system formation and Kuiper belt formation that they do not consider hypothetical planets. And we found that the results of these models, even the representative ones, they cannot explain these populations. For example, they are mutual intrinsic ratios and so on. And besides, we also actually perform a simulation to obtain independent results. So we perform a simulation considering only the current outer solar system, and we confirm that in such configuration, or even more slightly different scenarios, including planetary migration, they cannot explain well these observational constraints, these populations I just described. So our next step was actually to consider then, so how about if there is a hypothetical planet in a distant orbit that could perhaps explain better these populations? And actually the model published in this paper now is based on our actually a previous model which already considered a hypothetical planet published in 2008. It's quite a time ago, but surprisingly, after rereading my own paper, I found that several of the results and constraints we put there, they are still valid now. So that's the summary of the story. So we tested a hypothetical planet in the distant orbit. We tested many hypothetical orbits, small, large, medium, large, in terms of size. We tested different eccentricities to be, let's say, less elongated orbits, more elongated orbits. We tested very low inclination, 1 degree inclination, 30 degrees inclination. We also tested several different masses for this hypothetical planet. So we did a preliminary study to constrain the best combination of orbits and masses that could explain those mysterious populations of TNOs in the distant Kuiper belt. And then we found that an Earth-like planet with some orbit beyond 200 U, perhaps up to 500 or up to 800, and on an inclined orbit could yield the best results. They are not perfect, but they yield the best results that could roughly match the observations constraints I just summarized at the beginning of my description.
Now, finding and confirming this potential exoplanet, or I keep saying exoplanet, but it's actually a solar system planet, but finding it, will survey telescopes like the Vera Rubin Observatory that sees first light, I think, next year, will that be of help in trying to nail down and actually confirm it?
Yes, absolutely. Well, in our model, we have the problem that we cannot pinpoint preferred location in the sky to say, okay, the planet should be located over there. So that's a problem. The second problem is that at the moment we cannot also pinpoint where the planet would be in its orbit. If, let's say, near its closest approach to the sun, or on the opposite side of the orbit near its longest distance, the aphelion. So we cannot pinpoint it. That affects brightness that the planet would have, or more specifically, the apparent visual magnitude that as we measured. So in that case, if the orbit is more elongated, more eccentric, which seems to be the case, the results seems to indicate this is the case, it's more probable, based on Kepler laws, that the planet is currently orbiting near its aphelion, more distant point in its orbit than the perihelion. In that case, depending on the mass, if it's 1.5 Earth masses or up to 3, make some other reasonable assumptions, we can estimate the brightness in terms of visual magnitude. And it turns out that the planet could be, if it by chance it's near its perihelion, near 200 U or 250 U or something like that, it could appear as bright as, for example, dwarf planet Eris. So it could appear as a relatively bright object, but it's more probable to appear as a typical trans-Neptunian object with magnitudes of maybe 20, 21 magnitudes or something like that. So in that case, we would need a larger telescope, and not also a larger telescope to find a, let's say, fainter point in the sky, but also a wide scale observation. So we will need to observe the sky, large areas of the sky, because as I just mentioned, we cannot pinpoint, we cannot say there is a perfect region to observe. So basically, you would need to cover wider areas of the sky, trying to search for kind of relatively bright TNO, but perhaps quite faint, like 22 or 23 magnitudes is also possible. And in that case, the Vera Rubin telescope will help a lot, because they are going to observe large, huge areas of the sky, and they are going to track also such, let's say, fainter objects. They are like to pinpoint. And by the way, the object would be moving apparently in the sky very, very slowly because of its supposedly large distance. But in other words, it could be found by current technology, current telescopes, but that would require a lot of effort to cover wider areas of the sky. But the next generation of telescopes like Vera Rubin are like going to improve a lot this search. So I hope, if the planet is real, that it could be found within the next, let's say, 2-3 years or so, a few years from now.
I think we're going to find something out there, because, like I said, there's been talk of, the Planet Nine and this, but also maybe possibly a Mars-sized object explaining the Kuiper Cliff, and questions like that. So I think it's going to be really, really important, these survey telescopes, to to be able to look for movement, even as tiny as it is. But then again, if you've got computers that can, differentiate this stuff, you're not exactly like Clyde Tombaugh, with a blink comparator doing it by eye. You've got, algorithms and things like that can help you search. So do you think that the discovery will come from a computer?
Can I comment a little bit about the Kuiper cliff before answering your question?
Well, of course, by all means.
Okay, that's a very interesting point, because in 2008, when I first came out with this hypothetical idea, actually to explain the Kuiper belt, not the first time to propose a hypothetical plan. This comes back for more than 100 years ago. When I came with the idea to explain the entire Kuiper belt by the perturbations of a hypothetical planet, we also look at the Kuiper cliff problem, which interestingly and also intriguingly enough, it's still unsolved. And recently, I haven't seen in recent papers people trying to solve that problem. But we actually investigated if a planet could create the Kuiper cliff well. And by the way, in the early 2000s, there were a few studies that exactly look at that problem. And they propose, as exactly you mentioned, a Mars-sized planet located, let's say, at 60 AU, close enough to the Kuiper cliff, which is located at about 50 AU or so. And it turned out that such kind of planets, they don't exist. That was one of the conclusions we came in 2008, because if there were a Mars-sized planet located at 60 AU, even if it's on a high inclined orbit, in order to have escape detection by observations, because if it had a low inclination, it should have been discovered by now. So it should have a high inclination to have escape, or less probably just coincidentally located near the galactic plane, where usually observations they avoid this region. Anyway, from the dynamical perspective, we found that such a kind of planet probably does not exist, because although it could create the Kuiper cliff, at the same time it would destroy the stable resonant TNOs I just told at the beginning of our talk. In particular, 3-2, where, for example, Pluto is located, and also 2-1 stable resonant populations. They are prominent right now. So if you put, hypothetically, even a low mass Mars-sized planet at 60 AU or even 70 AU, if you will, the long-term perturbation of such a planet is going to destroy the stability of resonant TNOs in the 3-2 and 2-1 resonance. So because we see a permanent population in those locations, it's probably fair to say that we can rule out the existence of such kind of planets. So the Kuiper cliff is kind of a still open problem. In 2008, we tried to propose that the hypothetical planet, before acquiring its distant orbit, which may apply to the current model, because we didn't discuss how the origin of the orbit. But one idea that I, just like in the 2000 paper, I'd like to revisit in the near future is that this hypothetical planet probably formed in the region where the giant planets formed during the early solar system, about 4.5 billion years or so ago or so. So in that case, perhaps several objects, planetary objects with let's say tens of the Earth mass, or even Earth-like objects, they were scattered around it. So it's like a very chaotic phase of the solar system when the giant planets were forming. So perhaps one of these gravitationally scattered objects was the hypothetical planet. But during this temporary orbit interacting with the giant planets, maybe this interaction perturbed the primordial Kuiper belt in a way to create the Kuiper cliff. And actually, this was one of the results we found in 2008. It was possible to create the Kuiper cliff by temporarily planetary body being scattered by, for example, early formed Neptune. So this idea is around. It's still out there. It could work, but it needs to be revisited in light of the new observational constraints that I discussed in the beginning of our talk, and also in light of the new orbits and new preferred orbits and masses for the hypothetical planet as we discuss in the current paper. Okay, I just closed my parenthesis about the carbon cliffs. And your question, sorry, I forgot your question.
Well, I was just asking, do you think that when the search is on and you get some data, I mean, are you going to use computer algorithms and things like that to try to
Yeah.
get past the very, very slow motion of this object?
Yes.
Observationally speaking, yeah.
Yes, definitely. I think this machine learning and code and AI stuff, they are going to speed up a lot the search for very slowly moving objects, and also to use this data with data obtained by other telescopes like database in order to compare the data to see if the same object was observed and so on. So I think that in the next few years, especially when Vera Rubin is observing, getting a lot of data, they are going to revolutionize our search for such kind of objects. Even if the hypothetical is not discovered within the next few years, I'm sure that these surveys with their automatic search and find algorithms, they are going to find several new strange TNOs out there, maybe new sednas or even more, even objects with more surprising orbits that will that will puzzle the theorists and dynamicists like myself.
Now, there seems to be no real handle on just how many objects, like, Sedna or something like that, could be out there. Pluto-like objects and, trans-Neptunian objects. Could we be looking at like 100 or something like that of these minor planets out there?
Do you mean 100 like Sedna? Okay.
Yeah, I mean, is there any constraint on the upper end of the population of objects like that out there? I mean, is there, could we be looking at potentially hundreds of them, or is it probably going to be 10s to 20? Maybe we know about half of them right now, and we'll discover the other half. But as far as objects in that class of minor planet, I mean, could there be a bunch of them out there, or is it relatively constrained?
Okay. Well, of course, it depends on the size or the mass of the minor planet. There are some studies that constrain the number of primordial, for example, Earth-like size or Mars-sized objects, or even Pluto-sized objects during the early solar system. And from the top of my head, for example, Pluto-sized, or as if you will, dwarf planets, the number of primordial ones were probably on the order of thousands, maybe several thousand, but not more than not more than 10,000. So there are some studies that are more or less finding these numbers, maybe 4,000 or 5,000. So at the current solar system, we have discovered only 2 Pluto-sized dwarf planets, which are Pluto and Eris. So there are only 2. And so what happened to the other, let's say, 4,000 or 5,000? Probably several of them, they were lost, either by collisions with forming giant planets, or they were, perhaps several of them, they were gravitationally ejected by Jupiter, so they left the solar system. On the other hand, some of them were captured in more stable orbits in the Kuiper Belt, or even in the distant Kuiper Belt, or even perhaps near the Oort cloud at several thousand AU astronomical units. So it's difficult to predict the number of Pluto-sized objects at very distant orbits. But I would not be surprised if future surveys if they find, let's say, tens. I'm not sure if they find hundreds, but perhaps it will not be surprising to find tens of Pluto-sized dwarf planets out there in very distant orbits or very inclined orbits, and so on. It's very exciting to think about. And at the same time, on the same token, for example, the Mars-sized objects, they were less in numbers during the early solar system. So if they exist out there, they really would exist in smaller numbers, maybe tens, or maybe 10 or less than that. It's difficult to predict. So at the same time, we can mentioned about, we can also discuss about Earth-sized objects. So if there were tens of them, or maybe 100 or something like that during the solar system, several of them were lost and so on. So in that case, we could say that only one survived in our solar system, and that's exactly the hypothetical plan. That's the idea that perhaps one of these Earth-sized objects which existed in the early solar system, only one survived in the distant Kuiper belt. Perhaps, of course, it's possible that two or three survived, but in our working scenario, the idea is that just one could have survived in a stable orbit.
Now, about that, now this object could be Earth sized, a little bit more massive, of course, but could this be the solar system's super Earth, the missing super Earth that we see so commonly with other star systems that we don't have? Could this have been that? I mean, and moved out to a much further orbit at this point?
Well, it depends on how we define super Earth. So in the literature, in particular exoplanet literature, I realized that even planets with 2 or 3 times the mass of the Earth, they are collectively classified as super Earths. I am more a solar system researcher, so in my view, a super Earth is like a 5 Earth masses or more, which is also quite common in the exoplanetary database. But okay, if let's suppose that the hypothetical planet, as we propose in the paper, is 3 Earth masses. In that case, depending on how you define, you could say that it would be at the lower end of a super Earth, and in that case, it could be considered the missing super Earth of the solar system. But I personally, I think that the super Earth should be an object with mass more massive than Earth, the 5 Earth masses, which is actually one of this kind of, for example, massive objects are very commonly obtained in models that, for example, try to explain the formation of Uranus or Neptune. So this kind of what we call planetary embryos, so like 5 Earth masses, 4, 6, or something like that. They were probably the objects that ultimately, by some really large collisions, they formed essentially Neptune and Uranus. But that's my personal view, maybe because I'm influenced by solar system research.
Is it possible now, when you get an object that distant, which I think you set a perihelion of 200 AU, something like that, something that distant, could it be a capture just as easily as it could, be a native of our star system?
Yes, concerning the origin of the orbit of this putative planet. Yes, one idea, as I mentioned before, is that it was scattered out and by some chance dynamic interactions with other planetary bodies and so on, it acquired a stable orbit. The other possibility, as you mentioned, it could have maybe it was captured by, say, a system which passed close to the solar system during the early ages of the solar system, and it was fortuitously captured. It's possible. Perhaps it's a low probability event, although the scenario of scattering from the giant planet formation region to the outside is also probably a low probability event. So in that case, it's difficult to say which one is more probable. But anyway, yes, I think it's a possibility that the planet could have been captured from outside the solar system. Although we would need to check in more detail the probability, perhaps only a few percent, and then later also we need to follow to see the stability of such orbit, because as the solar system formed, it experienced many passing stars later during its, in particular, first billion years. So we would need to investigate if after capture such kind of planet would stay on a relatively stable orbit, or it could, or yeah, or if there is a chance that it could be stripped off from the solar system by similar mechanisms as passing stars and galactic tides and so on. But yes, I believe it's a possibility. Although personally, I'm I think that the scattering from Jupiter information region it's an interesting hypothesis because, as I mentioned before, we have more constraints on the numbers of objects that existed there. So it's probably a little bit more, maybe easier to investigate viability of this scenario because we can simulate several possibilities and several planetary bodies and then investigate dynamic evolution of such systems and so on. On the other hand, the capture scenario probably is is less is less constrained. So in that case, I think we know less about the environment that the solar system experienced during its infancy, during the first million years. So it's difficult because several models they assume that our solar system formed in a very dense star cluster, but other models they assume some different environments. So depending how you assume the environment of the passing stars and galactic tide, and also the influence of molecular clouds, they can produce quite different results. So in that case, it would alter the probability of capture, and I suppose also the probability of stripping off captured objects after the capture.
Say there is this planet, let's say it exists, and we find it. One of the biggest surprises of my time, having an interest in astronomy, which is almost 40 years now, is that Pluto turned out to be really dynamic and interesting. Way more than we thought. We used to think of it as an ice ball that, its atmosphere would freeze out and, during various times of its orbit. And we didn't realize that such an object can be so dynamic. So if we were able to go out and look at, say, a 2 Earth mass planet out there, it's going to be full of surprises, I would bet, right?
Yes, I believe so. As you said, Pluto. I also had this imagination. I also imagine Pluto as just maybe, with all respect to the dark planet, like a boring, icy ball in a very distant and cold orbit, and dark, and so on. But New Horizons mission changed our view completely. Now we know that Pluto is a very interesting, very dynamic place, and also even has several geological properties similar to Earth. So it was really really interesting to see the pictures and the results that still are being discussed. Concerning the Earth-like planet, so if it has a 2 Earth masses, I'm sure that it will reveal, if it exists, it will reveal very interesting physical properties, perhaps beyond our imagination. I try to imagine that a 2 Earth mass object first is going to have probably a very prominent internal energy source, for example, by the decay of radioactive elements, just as we have in our planet. So it's probably going to have very important internal energy source, and in that case, we could imagine. I know it's a little bit speculative, and we don't discuss this in the paper, so that's just a disclaimer. So in that case, we can imagine that the planet would have subsurface oceans. It's almost sure with such internal energy. I even speculate that perhaps because of such internal energy, perhaps the planet could have very active interactions between the subsurface and even the surface. Perhaps it could have more dynamical geological features compared to Pluto. Right? I would not be surprised if it could even have a tenuous atmosphere, and even from the perspective, from the extraterrestrial life perspective, maybe it could even contain some, I don't know, primitive organisms in its ocean and so on. So it could be even interesting in that regard. So in that sense, it would be like an Earth-like planet, not only because of similarity of size of mass with Earth, but also because of similarities in terms of geological properties and dynamics of subsurface and surface. Of course, having a very distant orbit would not imply an Earth-like planet, just like as we know here with nice temperatures and so on. The planet would probably have minus 200. I don't know. I'm not sure, but because of the interactions of the surface, it changed a little bit the subject, the temperatures. But anyway, we could imagine minus 230 or minus 220 degrees Celsius. It would be a very cold world, and the surface would be basically uh, an extreme version of Pluto with lots of different, not only water, but different ices frozen on the surface and so on. And probably mixed with important fractions of rock on the other hand. Because if this object formed near the region where the giant lands formed, we could expect that there was a contribution of rock components, not only ices, not only like water or methane, carbon monoxide oxygen. Not only that, but also some different substances, organics, and probably lots of different rocks mixed. But it would be a very, of course, surface frozen world. On the other hand, if the surface would be very active, we could expect perhaps some cryovolcanoes and also an extreme version of satellite Europa. We probably have lots of stripes and maybe water or whatever trying to interact with the surface from the subsurface. So I know it's speculative, but at the same time, it's perhaps not so far from what would be in reality if the planet exists. It would be a very interesting Earth-like, maybe an active, icy, rocky Earth-like planet out there. It would give us lots of hints about not only the physical properties, but also about the formation of the Kuiper Belt, the formation of the solar system, because we would need to understand also how it got there, how it acquired such an orbit. Yes, it would be very interesting to see if it's found in the near future.
It could turn out very easily that this and the other Kuiper Belt objects, because radioactive decay can keep an object like that warm, especially when we're talking about two Earth masses out that far. That not only do you have that, but you also have the organic chemistry out there that we see in cometary material, carbonaceous chondrites and things like that, and that
Yeah,
it's such a thing could be just as good as Europa or Enceladus as far as speculating about the potential for biology, because you certainly have what apparently is liquid water. But what interests me about that is that most of the oceanic environments that we think exist in the solar system are those kinds of places, ice shell moons, and maybe this is an ice shell planet. And that maybe that's the rule of the universe, and that the situation of Earth and the habitable zone and all that business is actually not where you would want to look for space whales or something like that, and that these ice shells are much more interesting, and it's all radioactive decay that's causing it, in the cores of these planets. I find that fascinating. I mean, does that fascinate you as well?
yes, definitely. It's fascinating. It's very interesting to imagine that not only the geochemistry and lots of probably different, not only the phenomena we know happening on Earth and Mars and the planets, terrestrial planets, but also different features and properties that could be also unique to such worlds. And at the same time, it's very interesting to think that if you look at if you imagine the surface of such moons or even such hypothetical objects, it probably it would be like frozen, not so probably not so prone to life. But if you just look a little bit within the below the surface, perhaps it could be a fantastic world of some microorganism or even more complex life if the conditions were favorable. Concerning the hypothetical planet, if we find such an object, it would be, I think, it's a very interesting target for even space exploration in order to find out not only the geological features or the geochemistry and even organic formation and so on, but also look at the subsurface, try to see what kind of environment we would find there. And I think it would also give us a lot of hints about the conditions and environments that could favor the formation, at least of the building blocks of life. That would be very interesting. It came to my mind also that I'm not familiar with the research, but there are some researchers also discussing the habitability of floating planets. So basically, it's a similar mechanism. So you look at the subsurface and try to see if there is some good conditions there for interesting chemistry or interesting exobiology. It's really fascinating, and I hope to be alive to witness such kind of discoveries, even if it's not a hypothetical planet, at least in our solar system. There are lots of interesting places still to look at.
My last question for you today is this, and this may even be more speculative than life, but not in a certain way. Volcanism in the outer solar system. Could an Earth mass or two Earth mass planet like that be volcanically active?
That's a good question. Again, it's a speculation, but my guess, based on what we know from our solar system, is that we would at least see cryovolcanoes, maybe a lot of them, and quite active. But perhaps it's not so far-fetched to think about even volcanoes similar to what we see in the Earth, or perhaps in the satellite Io, a different kind of volcanoes, depending on the magnitude of the interactions in the subsurface, and also, of course, the magnitude of the internal energy in such a large planet. So perhaps even different, not only cryovolcanoes, but all different volcanoes could be active. I don't see why this would be impossible, but that would be very exciting to see if it's real.
All right, Doctor, thank you for joining us today. And I will be watching your papers intently, and I hope you'll join us again. And I wish you good luck, and I look forward to the search for this new potential planet.
Yes, thank you very much for inviting me again. It was a pleasure to talk to you.